All right, we're going to go ahead and finish up with graphs today. Let me go ahead and actually, before we go to there, let's talk about what we've done with graphs so far. Just a good quick refresh, because graphs are very important. So actually doing a quick recap would be a good idea. And there's a nice, beautiful glare. All right. Okay, so let's say we had a graph 0, 1, 2, 3, 4, 5. And let's go ahead and get some points here. All right, give me some, how about some values?
11. 11.
11.
10.
Unique values. All right, nice, nice.
3.
3. 17.
11 divided by 2.
5.
And 4.
4. All right. Okay. So how do we represent this last time?
The 2D array.
With a 2D array, sometimes referred to as the matrix. And so we label it 0, 1, 2, 3, 4, and 5. 0, 1, 2, 3, 4, and 5. Nice and squeaky. Okay, and what was stored in each individual cell?
The value of the link between those two numbers.
Right, the value or the weight. Remember, each of these are called vertices or nodes. I like to call them nodes. Technically, the proper term is vertice. And the connection between your nodes or vertices is called an edge. And what's stored in here is the weight of each individual edge. Or basically, what is the cost from going from one vertice to another vertice? So, how about the cost from 0 to 0 is
0.
0. All right. What else can we fill out that's going to be 0?
It's the same.
5.
Yeah, all the way down. All right, obviously these are all zeros. Nice. Oh, that's a nice squeak this morning. All right. How about 0 to 1? 5. 0 to 2?
17.
All right, 17. 0 to 3? 3. 0 to 4?
Infinite.
Infinite. Yeah, we usually have whoops and the symbol to signify no connection, infinite or -1. 0 to 5? 1 to 0? Yep, still infinite, because remember these are directed. 1 to 2? 1 to 3?
Infinite.
Actually, yeah. They're all gonna be- Yeah, once you're at 1, you're kind of stuck. All right, 2 to 0?
Infinite all the way.
Yep. 2 is also stuck. How about 3 to 0?
Infinite.
Yep.
Only 3 to 5.
Yeah, only 3 to 5 as a number, and it is.
10.
I think you're starting to see what the problem here is.
4 graph.
How about 4?
4.
Yeah, 4.
4 to 0, of course, is infinite. Yep. How about 4 to 1?
4.
4. 4 to 2,
Infinite.
and are the rest infinite?
Yep.
All right. How about 5 to 0?
Infinite.
Actually, what's the only thing that's not infinite? 5 to 4? Yeah. Which is
11.
Okay. So, hopefully you can tell what's an issue here with using this data structure to represent a graph.
Sometimes things don't get connected.
And why is that an issue?
Like traversing, maybe, if you wanted to go to a child.
Okay. Well, if you want, what if you wanted to see all the children of one? What do you have to do?
Go to one.
Yeah, you go to this row and then you do what?
Iterate. row?
Yeah, you iterate through the row to find other children, only to find out that there's no children. Okay. Now for a 5 by 5, this may not be too bad. What if it's a million by a million?
An issue.
It's an issue,
All of
right?
unused values.
You have a lot of unused values, at least in this graph. A lot of graphs are what's called sparse graphs, where if you do the adjacency matrix, you don't have too many values filled in. In fact, the vast majority would be these infinite signs. So this is not very efficient, memory-wise, and it turns out to not be very efficient if you're trying to traverse the graph as well, because you have to go through the entire row just to find out that, oh wait, it doesn't have any children. So there should be a faster way. Can anyone think of what we should do instead?
Say if there's a, whether or not there's an edge.
Okay. So say whether or not there's an edge. So one would be
Would you say like no and then
no
yes?
edge. Okay, and this one might have, okay, you have an edge, and then what do you do afterwards?
Index through.
Okay. Well, so another way to think of this is you have an array of arrays, right? A vector of vectors. And so your vector has a set length. Now, it does make sense that you're still going to want to have a vector to represent every node. But what could you have instead of another vector to represent all the connections? A list, right. So if one right here was pointing to a list, what would that list be? Nothing. It'd be empty.
Yeah.
And if you wanted to traverse all the children of one, you wouldn't, it would be a very fast operation because it doesn't have any children and you're done. So that's actually what the next data structure for a graph is, and by the way, is the most oftenly used one for graphs, is to use a vector of lists. So let's do that real quick. Let's go over here, and we're going to go 0, 1, 2, 3, 4, 5. Let's do it this way. So this is the vector. This is just the index to them, and we're going to say what this points to. Now this is a little different than what's over here, so I'm going to put index. So it's clear that index 0 is pointing to a list. All right? Okay. So first off, do we need to know that 0 to 0 is 0? No, we don't need to throw that in there. That's superfluous. But what does need to go in here? 0 to 1, right? So now over here, we knew what edge or node we're going to by the index. Over here, we don't. So we actually have to store a pair. So for example, we might store 1, comma, 5. So going to 1 has a weight of 5. All right. How about the next one? What would it be?
217.
Yeah, there we go. 2, 17, 3, 3, and then are we done?
Yep.
Yep. How about 1? Empty set. How about 2? Empty set. How about 3?
5, 10.
Yep. About 4? 1, 4, right. Am I going off the screen? No. Beautiful. How about 5?
5, 5.
5, 5.
Could be
Oh, wait, no, that's
411.
That's a 0. Yeah.
411.
411. Don't listen.
And I trusted y'all.
I know. It looked kind of like a 5, so I was like, yeah. But that's a 0.
All right, there we go. All right. Which of these two data structures consumes less memory?
The list one.
The list does. All right, so it's definitely, in general, more memory efficient. Now, if it was a fully connected graph, meaning that there was an edge going from every node to every other node, which of these two would be more efficient memory-wise? The matrix. The matrix. But in general, most graphs are sparse, are somewhat sparse at least, semi-sparse. So this is going to be more memory efficient. Now, a couple other things here. Which is better, or in general, faster for traversal on a sparse graph? Let's just assume sparse graphs for now, and you want to traverse the entire graph. Which would you a guess would be faster to traverse? Why do you say the matrix?
Because it's an array of arrays.
Okay, I see where you're going with that, but think about it. If you want to visit all the nodes of 0, what do you have to do in the matrix? Go through the whole thing. All right, so you have 3 here and you have 5 over there. You want to go find all the children of 1, what do you have to do in the matrix? Go through the array. What do you have to do over here? Nothing. So if it's sparse, that means that these values over here, there's going to be fewer of them than the number that's filled in with the matrix. So which one, going back to traversal, where you have to investigate every single element over there in the matrix, which do you think is faster? The list. So the list is faster for traversing. Now, that's not to say the list is always better. What is a lot faster with the adjacency matrix? Adding? What do you mean by adding?
They're inserting.
Inserting.
Because you just have to apply like insert right at the ends.
Okay.
That's it.
So with the matrix, actually adding to the matrix or adding an edge is what you're trying to say?
Yeah.
Yeah. To a matrix, yeah, you just jump to the edge of the matrix, you put the value in, you're done, so it's O of 1. Although over here, if you want to add something, actually what do you need to do?
You have to find its position there.
Yeah, you first, well, you don't have to find its position, but you have to find out, is it already in there?
Yeah.
In general, you can assume it's not. So you can just add to the end of the list, and maybe that's okay. So inserting in general is faster, but in addition to inserting, what's the opposite of inserting? Pulling it out. So if you want to find out what's the weight between 2 nodes, in the matrix, you just jump to the cell, and now you have the answer. Over here, you have to jump to the list and then go through the entire list. So here we go. Which of these 2 is better? Oh, yes, thank you. No! All right, it depends. What does it depend on? What do you think?
What you're using.
Okay, nice, nice. But which patterns of use would you want to use the matrix over the list?
We would want to use the matrix if we had a lot of values.
If you had a lot of values in general, yes.
They're all connected.
If it's a fully connected graph, then yeah, you definitely want to use all the values. But thinking from a big O perspective, which one? Remember what operations did I just talk about? If you're doing a lot of inserting of edges, or you're doing a lot of what's the weight between these 2 edges, the matrix is going to be better. But when is the list going to be better?
The rest of the time.
Rest of the time.
You need to traverse.
When you need to traverse the graph, like you're over here and you need to figure out where you need to go in the graph. Now, what ends up happening is most of the time with your graph algorithms, you're doing some type of traversal, which is why most of the time you want to use an adjacency list in order to represent a graph. I know I did the matrix first. I think the matrix is a little more intuitive at first and easier to understand what's going on. But the list is what's used most of the time. All right. And that was the 15-minute explanation. Let me go ahead and pause it, and then we're going to go through the slides.